Okay, we're back at it with hyperbolas, so let's take a look at this next example. This one, I look at it and I think, how do I know what that is? I know what that is because both the x and the y are squared. They have opposite signs, meaning one's positive, the other is negative. That tells me I have a hyperbola. So that's kind of what we're looking at here. To be able to get it in standard form, I have to complete the square. So I'm going to group my x's, just like I did on the ellipse one. Group the y's, minus y squared, minus 4y. Add 4, I'm not actually ready to complete the square yet. Add 4 over. I left some space there because I was thinking I would complete the square on that, but I need my coefficient to be 1. So I have to factor out a 4 on the x's and a -1 on the y's. And then I can complete the square in this open space I have here. Take the b, divide it by 2. 2 over 2, square that, you get 1 plus 1. I added a net of 4 to this side, so I have to add 4 to the right side also. I did not bring that 4 down correctly, did I? I have a 4 here, not a 0. Okay. So when I add 1 here and have that factor of 4 out front, I added 4 to the left side. I have to add 4 to the right side. This one, I take the b, which is 4, divide it by 2, and square it, and I get 2 squared, or 4. So I'm going to add 4 here, which is a net gain of subtracting 4. That leaves me 4 times x plus 1 quantity squared minus y plus 2 squared equals 4. That's good in that it gets me to the close to the standard form of a hyperbola. I know with that subtraction between them, I have a hyperbola, not an ellipse. I want a 1, though, on the right side. So I'm going to divide both sides of this by 4. I get x plus 1 squared minus y plus 2 quantity squared over 4 equaling 1. That tells me my center is -1, -2. I am very visual, so I need a picture here to help me with this. I don't think I could answer these other questions just because I don't like to memorize those formulas. If you memorize those formulas, you may be able to do that, but I am not a memorize a formula kind of person. So I am going to plot this. -1, -2 would be here. And what other piece of information do I know? This is going to open left and right because the x is positive. By the way, if we had ended up with a negative number on the right side over here, we would have just divided by that negative. It would have switched the x's and the y's, and it would have opened the other way. I go over to the right 1 space because this is over 1. I go up 2 spaces and down 2 spaces to complete my rectangle here. So my asymptotes, oh, that should be right on the axis. My asymptotes are here and here. I don't really necessarily need all of this, but for me, it makes me feel much more comfortable in getting my picture to get the other information that I need. It asks me for the vertices, the foci, and the asymptotes. So let's start with the vertices. Here and here one to the right and one to the left of the center changes the x value, not the y value. So those are my vertices. The asymptotes we can probably do here. The rise, so for my asymptotes, my slope will be, my rise is 2, my run is 1. So it'll be plus or minus 2 for my two asymptotes, positive 2, negative 2. So my equation would be y minus, let's see, my center is on them, so plus 2 equals plus or minus 2 times x plus 1, filling in that center for the x1 and the y1. That's my asymptotes. Here's my vertices. What's left? Foci, right? So let's say c squared. Remember, the foci is going to be somewhere out here and somewhere out here. Has to equal 1 plus 4. So c squared is 5. C equals the square root of 5, which is a little more than 2, right? So from the center, that would be a distance of 2, a little bit more than that. 1, 2, a little bit more than that. That's where my foci are going to be. Let's name those ordered pairs. Notice the x coordinate of the center is what's changing because I am going left and right from the center. My y coordinate is still negative 2. I take the negative 1 and I add root 5. I take the negative 1 and I subtract root 5. Okay, that one is a little different because it was written in this expanded out form, right? So we had to complete the square to get it into a form that we could actually work with. Let's talk about where hyperbolas are used. They are used in architecture. You will see them like a cooling tower. A sonic boom is another example. The pattern of that cone that is created after a sonic boom, that sound wave that is created, how it intersects the ground is hyperbolic. So this shape here, because it's that cone intersecting with a plane, the ground, right? And that's the definition of a hyperbola graphically, geometrically. Same thing with a light on a wall. If you've ever looked at like a circular lampshade next to a wall, this reflection here and down here are hyperbolic. Same thing here, where this cone intersects the ground is a hyperbola or part of a hyperbola there. A little bit more about the eccentricity. Same thing, you can calculate it as c over a. So this e is c over a. These numbers, because the c is always bigger than a, these numbers will be bigger than 1. So notice here the narrower the hyperbola, the smaller the number. The more flattened and spread out it gets, the bigger the number, because the c gets bigger compared to the a. Okay, that's a couple of things with hyperbolas. Let's actually do an example using this. It says an explosion is recorded by 2 microphones that are 1 mile apart. Microphone M1 received the sound 2 seconds before microphone M2. Assuming sound travels at 1,100 feet per second, determine the possible locations of the explosion relative to the location of the microphones. Well, here's our picture. We have these microphones, right? just for space. I'm going to put this microphone 1 and this microphone 2. They are 1 mile apart. I am going to make my own little coordinate plane here. I can set that however I want. I'm going to have the y-axis go right between them and the x-axis go here. So at this point right here is the origin. Microphone M1 received the sound 2 seconds before microphone M2. Let's suppose the explosion is, I don't know, let's say it's here, okay? At some point XY. What's happening here is this distance and this distance, let's call this D1 and this D2. D1 has to be 2,200 feet more than D2. Whatever this distance is, this distance here is 2,200 feet more than that. How did I get that? Well, if sound travels at 1,100 feet per second, and it took 2 more seconds to get over to microphone 2, then that's 2,200 feet. 1,100 feet for 1 second would be 2,200 feet for 2 seconds. That implies that D1 minus D2 is 2,200. Wherever this explosion is, right? I don't have a specific point that that explosion is at. I'm just drawing a general picture here. So we're looking for the set of points, the locus of points that satisfy this definition. That's exactly the definition of a hyperbola, right? Where that distance, the difference in the distances is constant. It is always the same number, in this case 2,200 feet. That tells me I have a hyperbola here. We also know that that has to be, when that's a hyperbola, that number is actually equal to 2a. And the reason we know that is because this distance and this distance are both a, right? And so if this explosion was right here, let's say the explosion was right at microphone 1, well, we have to go that 2,200 feet. So the distance between them is 2,200, or this is 1,100. Okay, I'm sort of assuming it doesn't really matter, but I'm forcing my hyperbola to open sideways just because of the way I've oriented this. I could completely change this picture, rotate it 90 degrees, where my mic 1 and mic 2 were vertical, right? But in this case, x squared and y squared in the numerator with the x squared first, I'm forcing my center to be 0, 0, right? I can choose that. So equal to 1. Now I need to know what numbers go below here. Well, this is 1,100 squared, right? That's the A. Under here is the B, where I have this relationship of C squared equals A squared plus B squared, right? So hold on, my picture's not exactly right here. My hyperbola is not going to go through the microphones. Those are the foci. That's where those fixed points are, right? Sorry about that. The fixed points in our definition of the hyperbola, where the difference between them, those are at the foci. So let me erase this. This picture's not quite right here. This is 1100 and this is 1100. This right here, the distance to the microphone, we know those mics are 1 mile apart. So we need to be in terms of feet because everything else is in terms of feet. So this will be half a mile, which is 5,280 feet divided by 2, or 2640. That's going to be my C. 2,640, 1,100, and then the B squared, which is what we need to put in here, is what we need to find. 2640 squared, 696, so 6,969,600 minus 1,100 is 1,210,000. When you do that subtraction, you get B squared is 5,759,600. 575, yeah. That's what's going to go here, B squared. 5,759,600. Let's just clean this up a little bit. Multiply that out. So what we know, we don't know where this explosion is. It's at some ordered pair x, y, where the relationship between x and y is that, because it has to be on this hyperbola, because the difference between those distances from the mic to the explosion is constant. That's our definition of a hyperbola. Did we answer the question? I always like to make sure. Determine the possible locations of the explosion relative to the location of the mics. Yep, we did. It's at some ordered pair x, y on the right arm of this. It has to be at the one, on the one closer to mic 1, right? Because mic 1 heard it first. It has to be over here. It can't be on this part of the hyperbola over there. Okay, that's our applications of hyperbolas. That is our third conic section we are going to talk about. Our last conic section is actually the parabola. We have studied parabolas pretty extensively already. We're going to study them from a little different perspective, a geometric perspective, in our next video.